Cool, wonderful. So hey everyone, for those who don't know me, I'm Jacob. I'm the president of SIGAI. This is our first reading group of the semester, so thank you all for coming. So this year we're trying something a little bit experimental. In previous semester, we were mostly going over state-of-the-art papers in robotics and computer vision. This time we're going to be going over a chapter in a math textbook related to so the whole point of the reading group is to keep up with the state of the art and make sure that we understand the state of the art as well. So we thought that this might be a worthwhile addition to the reading group. It's not your cup of tea. You can tell us. We're going to send out a survey after this to see if you guys would rather go over papers or go on with the math textbook, or maybe just start branching out and start another reading group with the math textbook. Cool. With that.
Okay. Fantastic. I hope you guys had a great break. Today we're going to be talking about math within the context of deep learning. There is a lot of, to develop a machine learning model, right, from start to finish is very, very easy with your TensorFlow, PyTorch packages. It doesn't require a lot of understanding of the math. As long as you are able to use the library well, it's very easy for us to sort of build a classifier that performs reasonably well. However, at its core, machine learning is math, right? And the intuition behind this was that understanding the math will allow us to use and leverage the framework better, more than just giving API calls, but also understanding why it works the way it does, so that we can build models and set them up to succeed in ways that are more sophisticated than a traditional pipeline. And the first, so this book that we are using, it is from a bunch of professors who basically got together and decided to compile the most verbose source possible. So we're basically just using that as our guiding star. The first chapter covers three algebraic structures, and we'll go over algebraic structures are, so don't worry about that. But the three things that we're going to be covering today are groups, rings, and fields. And these three data structures build up to another data structure, which is the vector space. And the vector space is a large focus of this book. The groups, rings, and fields are merely an introduction. So what are algebraic structures at its core, right? Algebraic, actually I should use the book for this. Okay, so let's start off with algebraic structures and what they fundamentally are, right? An algebraic structure is quite similar at its core to a data structure, right? We learn about data structures in CS 251. This is basically the math version of that. It is a collection of objects, right? And these objects, they can be matrices, they can be functions, they can be integers, rational numbers, basically anything, real numbers, anything, complex numbers, everything works, right? And these collections can have a series of operations that we can perform on them, right? And these operations and the properties of these operations, like the number of the operations and the type of the operations, are the basis for what algebraic structures are. And these algebraic structures, the existence of these algebraic structures allows us to do three fundamental things, right? The first is it acts as a basis for categorization. So as I mentioned previously, the type of the algebraic structure, so the group, ring, field, vector space, etc., it allows us to draw connections between two different algebraic structures. So as you see, groups are very closely related to fields, which are very closely related to rings, which are subsequently closely related to vector spaces. And that sort of connection allows us to draw inferences and basically extrapolate on what that fundamental data structure is. So we can basically discover or use that to discover systems with similar properties and extrapolate that to algebraic structures that they do not even exist. So if we understand or build a theorem for one given algebraic structure, we can extrapolate that to all of the other data structures that it supposedly extends. And it will make a lot more sense as we go forward. So the three things that it allows us to achieve is first the basis for categorization. And if I can write faster, that would be fantastic. Then it allows us to draw connections between algebraic structures and finally the theorems on one structure, extrapolate to unknown structures. Right. And it's so this final bit, right, with the extrapolation, it firmly depends on the ability to, or like it firmly depends on a couple of axioms, right? And these axioms are basically the basic properties that define a given data structure. So these are the three utilities. They have some sort of similarity to data structures when we begin to define them. Yeah. Sure. Better? Okay. So yeah, where was I? Relation to data structures. So now similarly to actual data structures within computer science, right? We are going to be able to see or define some abstract data types wherein we assign it maybe an operation, and this operation could be any operation. It could be plus, it could be multiplication, it could be division and subtraction in abstract data structures that we are basically, or abstract algebra, which is the domain under which we're studying, is not technically defined. We use something called the additive inverse, which is a generalization on subtraction, and the multiplicative inverse, which is an abstraction of division. And the inverse, to define it more concretely, is effectively, well, we have additive and we have multiplicative, right? And if we were to get the additive inverse, if for x, that would basically be negative x, and the multiplicative inverse for say x over y will be y over x. And the idea here is that when you perform an addition with the additive inverse and a multiplication with the multiplicative inverse, you should get the identity of that given operand, right? So the identity is effectively the value by which or against which you can perform an operation, and it doesn't change the value of the, or it doesn't basically change the original value. So x plus 0 is x, and this is basically over here, 0 is basically our identity. And if you want to do it, okay, visible, yes. For multiplication, x divided by y times 1 is also x over y, so it's basically the same thing. And this is the multiplicative identity. So these are our basics. We can probably start off with a data structure now, or an algebraic structure now. So the first one that we have are groups, right? And groups are well, let's take it from our base algebraic structure. So in this case, we have our base component of, or like a base component as we define it over here, as a collection of objects. So groups are also deriving from that a collection of objects, and this collection of objects will have certain properties. This collection of objects will have certain properties that separates it from the base algebraic structure, right? And that base algebraic structure has an operation that it can run, and that operation is arbitrarily defined. And in this case, I am going to just set that as the plus icon with a circle around it. This can represent anything. It can represent multiplication. It can represent addition, basically anything, right? And this group can has the following properties of this individual operation, right? This individual operation needs to be or needs to have the following properties. Firstly, it needs to be associative, which means any operation that is done within the objects within this particular group should be associative. In that, A plus, say, B plus C should be equal to A plus B, and then this in parentheses plus C. And over here, A, B, and C all belong to group G, right? So we can define an arbitrary group G, and A, B, C are all elements within that particular group, and they have the property of associativity. The second is something we discussed before, which is the identity or the existence of an identity. So anything, so A with the operation times an identity, in this case we basically give it an eigen E because we don't know if it is multiplication or addition, right? So this also becomes a variable, and then when any operation that is done against this identity variable should net us our original variable. Again, A belongs to the group G. So it needs to be associative, it needs to have an identity, and finally, it needs to have an inverse. So what I mean by an inverse is also, again, something that we discussed before, right? We have our additive inverse over here and our multiplicative inverse over here. The inverse, in a more technical definition, really is just the element when operated against the inverse gives the identity. So we basically define our inverse as the resultant, or sorry, yeah, so we basically define our identity as the resultant of, oh lovely, okay, yeah. So if A minus 1 or A raised to negative 1 exists within our group G, it matches or meets the inverse property, right? And the operations within this group G are closed. And what that means is, if we have operator A and we run that against an operator B, we get an operator C. This operator C also belongs to our group G, which is the definition of closed. Yeah.
The 0 and 1 identity elements have their inverses as well, because theoretically 0 divided by 0 does not exist.
Yeah, that is an exception. So within the like the operators or the operations that are defined for the algebraic structure like a group, we basically omit the inverses for the identity itself. However, for rings, we have a specific property which we will get to, wherein we explicitly include the identity within the algebraic structure as a property. However, it is contested. So what that means is that some people believe that it should be present and should not be present. The reasons for which are above my level. So I couldn't give you a reasonable answer for that. But yeah, that was a good question. And I should have mentioned that. So if we have a collection of objects that meet these three properties, we get a group. That terminates our definition of a group. If it does not meet this inverse property and only meets these two properties, the of being associative and having an identity, we get a monoid, which is another sub algebraic structure. However, it is only mentioned in passing in the book, so I do not know how relevant it actually is. So, but they did mention it, so I figured I might as well let you guys know. So, a couple of examples for a group, right? We have the set of integers with the operator or the operation over here being just addition, right? So if you were to sort of check this, we have element zero, like not zero, let's say 4 plus 2 plus 1 will be the same as 4 plus 2 plus 1 with a different parentheses, right? That's our associative done. The existence of an identity, 4 plus 0 is equal to 4. That's our identity. And the existence of our inverse, so 4 and plus minus 4, which is our inverse, will give us our identity, which is 0. So we basically get these three properties fulfilled, which gives us the fact that Z with the operator of plus is a group, right? If we were to get an example of a monoid right up there, we could basically just say the set of natural numbers is that of a monoid, right? Because natural numbers go 0, 1. Oh, does it include? Yeah, natural includes. Natural does not. Okay, then whole includes 0, right? Whole numbers include 0, right? My bad. Okay, so the set of whole numbers that includes 0 and goes all the way up to countable infinity is an example of a monoid, because it does meet the associative property, which is basically the same as over here, and the existence of an identity also the same. It matches the one that is present over here. However, since negative numbers do not exist within this set of whole numbers, it does not meet the final third property and is a monoid. Yes.
So can you have multiple operations?
Yes. So within groups, you can have only one operation. That one operation can differ, right? It can be a multiplicative operation or an additive operation. However, we have the other data structures, as different structures that we will explore, like rings. They have multiple operations defined with them. So another example that pops up very frequently actually is the set of integers with a mod n, and the existence of mod n is basically a subset of your series of numbers. So it's basically the operation from computer science, right? So if I have, let's assume our mod is 7, we take 8 mod 7, we are going to get 1. So this is basically the series of whole integers that let me just say that one more time. It is the series of integers on which we perform a modulus operation, right? That's basically it. And if this also meets the criteria of being a group, so if we perform additive operations on on any number within the integer space with modulo n, and n can be also any positive number, we will get a valid series. It will satisfy associative, existence, and inverse criterions. And I guess the last example that I have prepared for you guys is that of a matrix, and GL is basically the abbreviation for the function, and this matrix is a 2 by 2 square matrix on the set of real numbers. And the important criterion within this is that these matrices need to be defined as invertible, because if they are not invertible, it will be impossible for an identity to exist of the given matrix. And this also meets the associative criteria, because A dot B and then in parentheses B dot C is the same as A dot B in parentheses dot product with C. However, this operation, right, or matrix 2 by 2 matrix operations are not necessarily commutative. So A dot B does not necessarily equal to B dot A, and that is something that is important to consider. Since the commutative property is not defined within a group, we don't need to. Okay, sorry about that. Please let me know next time. But since the commutative property is not defined within a group, we don't need to worry about it, right? And if it does satisfy the commutative property, in that case, it is called a abelian group or a commutative group. So abelian commutative group. If A dot B is equal to B dot A. Okay, so that concludes our discussion for the first algebraic structure. Do I have any questions? Yes.
So you don't necessarily need to have iterative, but if you do have iterative rule, it doesn't change the structure.
No, it does not change into a different structure. It's basically, it's just called a different name. And the reason that we are talking about the existence of an abelian or a commutative group is because it's relevant for the data structures that we follow, right? And this is the group is the fundamental data structure for abstract algebra as a domain, and everything to some extent builds off of a group, as we will see very, very soon. So this is very, very critical. So does everything make sense so far? Yes.
Three questions. One, is the empty set considered a group? Two, is the set with only the zero element considered a group?
Okay. Well, that is a good.
Empty set doesn't make sense because the identity element does not exist.
Right.
But the set with only element zero, the only problem is that the existence of additive and the inverses, because you don't have a multiple.
Right. Well, so the thing is, so over here with the real numbers, right? We define it as existing with a plus operation. We don't need to have both multiplicative and additive setups. So if we we have an empty, not empty set, but a zero set, right? It will be associative, right? It will be closed. The identity will exist, and we can get I guess we cannot get an additive inverse because minus zero does not exist, but I could not tell you for sure, because by definition any two numbers that will get us our identity, which is zero, so 0 plus 0 gives us 0. Technically, if we do not define the inverse as being something or like following a certain pattern, right? So even if we don't define -0, as long as it gets our as long as it gets our identity operand, I think it should be a group. Is multiplication 6 and nothing about addition? Huh. That's interesting. How would it? Okay, so how would it work for? Yeah, but like this would work for multiplication too, right? I mean 0 times 0 and then 0 times 0 times 0 in parentheses, nothing changes.
But zero divided by zero.
Right. Well,
That's your inverse.
if we define, okay, yeah. Okay, we should take a look at this. Can you send it on like the link on the reading group chat? Okay, awesome. What's next? So, following the group data or like algebraic structure, we have rings, and rings are an extension of groups, right? And the way that, okay, let's just write this down. They are an extension of groups, and the way that they extend groups is by using two operations or defining two operations. And the same as last time, right? I am going to set up an operator plus with a circle and another operator dot with a circle. Both of these operators exist and could be anything, and as long as they fit within our criteria, they work. We will be today in this discussion, we're going to be talking about plus as addition and dot as multiplication, because that was what was mentioned in the book. And yeah, both of these operations are closed operations, which is the same as what we discussed with groups, wherein if we have A plus B and we get C, this all of A, B, and C belong to group G, or in this case, ring R, right? And for the dot product, we can get much of the same when in A dot B is C and this same condition is met. So in this case also, it is closed. We already discussed inverses, and okay. Let's talk about the addition operation and the properties that the addition operation has. So firstly, we discussed the associative property, and this holds true again, so I won't bother rewriting it. It does have the inverse property, so existence of an inverse, so an inverse should exist. We should have, we already discussed the fact that it is closed, but the thing that we did not discuss is the fact that rings are defined as or the operations within rings, at least the additive operations within rings, are set up as commutative, which means a group or a abelian group is what technically extends into rings and not just any other group. So over here, the additional property is that we have abelian or commutative groups. And to make this more explicit, we perform the additive operation and if we basically get the reverse order, it should still stand and give us the same output. An important thing to note with regards to this is that while we define x plus y or x operate or these two operations, right, we are basically picking up x comma y as a pair out of our ring. So if we were to sort of get this x comma y pair, we could represent the extraction process as r cross r, where where we would get x comma y, and the additive operation would give us our output, which is this, right? And while we have this sort of operation that we have defined as commutative, this does not mean that the pairs that we extract over here are also commutative. The only thing that this commutative property says is that when a pair is provided for a given operation, it returns an output regardless of the order of that output, and does not comment on the pairwise extraction of the particular ring. In our case, we have only one ring from which we are extracting values. However, if it was another ring, so let's say we have ring A over here and ring B over here, the values that we will get from X will not be, we cannot basically reverse them because they are extracted from a different algebraic structure. So that is an important thing to keep in mind when we define anything as commutative or associative, and basically anywhere where we define the fact that the order does not matter, it only reflects that of the operation and not that of the source of the data. Sweet. So that, and I'll also explicitly write closed operation, although we did define it generally before. Okay, that is the first operation of a ring that we have defined, and the second one is that of multiplication. And the multiplicative properties, they do not have a name. So right now we define associative, inverse, abelian, or commutative properties, but that does not exist for the dot product. And the reason for that is the operations that we carry out in here are a mix of algebraic structures, right? We can have, as a part of the collection within an algebraic structure, we can have a matrix and we can also have an integer. So if we have an operation between an integer and a matrix, we cannot use the standard dot product operator. So in which case we use the dot with the circle. So the dot with the circle is just a generalization. You can view it as the same, but algebraic notation basically expects us to use it in such a way that we define it. We explicitly speak about what the differences are. So while the properties still exist and are similar, and I will write them down as similar, they do not actually exist. So please just keep that in mind. So for multiplicative, we also define an associative property wherein this dot b dot, oh god, this is so horrible. Apologies. B dot c is the same as a dot b dot c. We already defined the closed property, and that is exactly the same. I will not bother writing that one out. We have actually an important thing to note as well over here is that while we have these four properties for the additive operation, for the multiplicative operation, there are only two things that are actually required, right? And those two things are the fact that it is one associative and second closed. And by closed, again, I mean A dot B gives us C, and all of A, B, and C belong to the ring. Right? I'm just repeating myself basically. So these two properties, assuming these two properties are met for the multiplicative operation, and these four properties are met for the additive operation, we will basically get our complete ring. Now, there are many different types of rings. So while we define our base ring as this, we have additional types of rings with optional components that we basically will define over here. So if our ring is commutative, we get a commutative ring. So again, this is optional. And whenever anything is optional, I'm just going to put a question mark or the equal to over here. And this will give us a commutative ring. Oh, sorry, not visible. But yeah, A dot B, I have the question mark over here. If it is an optional dependency, B dot A, because this is the commutative property. Okay. Then the next one is another one that we have discussed, which is the existence of an inverse. So this also is an optional dependency, and in the cases where we do have an inverse, wait, is there a name for this? Okay, yeah. If there exists a multiplicative inverse, that is actually very, very important to rings because it allows us to basically define a division operation or the multiplicative inverse. Because we do not expect the inverse of any element within a ring to exist. That basically means that it basically prevents us from performing division, because we define multiplicate or division as the multiplicative inverse, and if the inverse does not exist, we basically cannot divide. So a special type of ring wherein this multiplicative inverse exists is called a division ring. That I think covers it for the different types of rings. We have the commutative ring and the division ring. And interestingly, right, if we have a ring that is both commutative and contains an inverse, that gives us our third algebraic structure that we'll talk about, which is fields. And that definition is basically ingrained into that of a ring. So it is possible for a commutative non-inverse ring to exist. But if it does, it's a field. Commutative invertible elements. Right. So that was rings.
So it says commutative non-inverse.
Yeah. So
Did you mean
it's
commutative and inverse?
no. So it's possible for such a type of ring to exist, and that's just a ring. That is separate from the definition of field.
I'm sorry, but I just wrote this close together. So
Yeah, that's my bad. So yeah, we can have a commutative uninvertible ring, and that's okay. That exists, but if it does invert, and I should explain make that explicit as well. It's a field, which is our next algebraic structure. Okay, so folks, questions for me. Does everything make sense? Everything make a little sense? Okay, cool. Let's talk about fields. Give me a second. Okay, so let's start with fields. The basic definition, well, first off, it is an extension of a ring or of rings, and we define formally a field F as a set on which two operations can be run. Again, we define those two operations as plus and the dot with the circle, right? Since we already discussed, or we already have a basic idea of what fields are, in that they are invertible commutative rings, we won't sort of specify or explicitly state all of the properties that exist. However, we will discuss the relation of fields with that of groups. So fields are basically two groups combined into one, right? A additive operation. This is the subset of a field with an additive operation. This gives us a commutative group, and the subset of F with the multiplicative operation is another commutative group. And these the properties within the field, or these two operations within the field as well as the ring, are linked together by the distributive property, which basically states that A dot B plus C is basically the expansion for this, and that is the distributive property. They also defined it in the book. Yeah, they also defined it in the book with the sort of opposite way, just to show that this works too, wherein we have the A dot C plus B dot C, right? And did I set up? Yeah. So there are a couple of examples as well for fields, and fields. Okay, there are a couple of examples for fields. One of which is that of the set of all rational numbers, the set of all real numbers, and the set of all complex numbers. There are very famous fields and basically meet all of these criterion. If we were to generally define sort of the operations that we could carry out on all of the algebraic structures that we discussed, we can loosely put it like this. So very loosely speaking, if we can perform additive and additive inverse operations on a given collection of objects, we have ourselves a group. And if we can say perform multiplicative operations on the collection of objects, we get a ring. And if we extend that even further to include the division or multiplicative inverse operation, we get a field. And that basically is the dichotomy of these algebraic structures. We have been working a lot throughout our middle school, high school, with the working under the assumption that all of these four operations are universally possible, but in a lot of cases it is not possible to perform all of these known operations. And this basically explores that specific dichotomy. Something interesting with regards to that of the fields are prime fields, wherein we define a field over a modulus n, and this modulus could basically be anything. And the set of integers over modulo n does not necessarily meet the definition for a field. It is not always possible to perform every single operation on a field. However, or on a given set, right? However, we were able, or like the book mentioned this really cool relation wherein we were able to define all, or like certain moduluses did classify as fields, while some others did not. And the interesting thing about those that classified as fields were that they were all prime numbers. So if this n over here is a prime number, then it is a field. Otherwise, it is a ring. It is quite a curious correlation. I did not quite understand why that was the case, but it was pretty interesting. So I figured I might as well let you guys know. One more thing, or to just make more explicit the fact that complex numbers, so for not complex numbers, rational numbers with root 2, with any given root, for instance, also belong to a field. We use the rationalization trick, right, to make sure that it is no longer an irrational number. For instance, if we were to obtain the identity of, say, a root 2 plus b, right, we need a number, say 3 root 2 plus 4. If we were to obtain any number that you can multiply this with such that you get your inverse of 1, you would basically obtain that by first getting the genuine inverse of this, which is 1 over 3 root 2 plus 4, and then making this irrational fraction rational using just the negative of it. So the numerator and the denominator are both the, I don't know, it's the rationalization trick. I don't know what the technical term is, but you basically do this, and I think, what is it, 18 and 16, so this will give you 2, and that is a rational fraction. So that is basically the rational trick, or the rationalization trick that they use in order to make sure that even numbers with irrational roots, or roots that are not integers, are are valid fields. So that is all that I have set up for today. Let me just check the pipeline. Got 200. Right. Yeah. Okay. So yes, that is all that I have from chapter 2. Chapter 3 covers vector spaces, and that we will cover on the basis of the poles. So yeah, that is what I have for you guys. Do we have any questions? Nothing? Okay. Thank you very much. I hope you enjoyed, and yeah, have a good rest.